evening, everyone. Welcome to Takeo After Dark commercial type version, whatever you want to call it. My name is Brett Zerba. I'm an applications/training engineer with Takeo, and I will be moderating today's event, tonight's event. Hopefully it's after dark where you are, but I based on some of the names I see here, I think some of the folks are probably still see the sun out, but I definitely do not see the sun where I am. I did see a nice sunset tonight. It was very, very, very pretty. Tonight's topic is going to be a discussion on introduction to air source heat pump systems. You know, what are they? Hydronics. And I see some folks on here that probably know as much, if not more, than Rich and I about this topic. So I'm sure they will add to the topic. But if you could raise your hands to make sure you can hear me and see me. A couple folks, if they raise their hands. Thank you. I see some folks raising their hands, so that's a good sign. And Rich is quite the artist tonight. Oh my God, yeah, he's stepping up. He's stepping up his game. Although his daughter's a music teacher, I think she dabbles in art. She may have done some teaching for Rich on this subject tonight. So tonight's, we're going to have some fun. We're going to teach. We're going to learn. Hopefully I learn some more, you learn some more, Rich learns some more, but ask questions. I'll be moderating the questions as they come up. We want to keep this light. We want to make it educational, but we also want to make it fun. That's the owner of Takeo, Johnny White Jr. He says, if it's not fun, it's not worth it. So he has made that quote in the past. So let's make sure we have some fun tonight. And as most of you know, Takeo is a privately held company, third generation, 102 years old now. Christ, we started these programs and we were only 100 years old. The pandemic, oh my God, let's not even talk about that. Let's move on from that. But nonetheless, headquarters in Cranston, Rhode Island. Rich was recently up to our Canada facility. We have a facility in Milton, Canada, not far from the Toronto airport outside of Toronto. So, and we've actually had a presence in Canada for over 90 years. Not everybody knows that, so God bless for that. We are a worldwide company, and I can't emphasize enough how much Cheryl Merchant and her staff has done. Cheryl is the COO. Oh, maybe I said that wrong. I always get confused, but she's a very important president and leader of our company, worldwide company, and what her staff has done, her team has done to lead us through this past couple of years has been phenomenal. Some of you may have met her in the past or seen her at ASHRAE. We had a nice booth at ASHRAE in Las Vegas a couple of weeks ago. It's probably a month ago already, for God's sakes. That's how time flies. But she was there, and she was saying hi to everybody, and did a nice presentation as well. So 24 hours from now, if you need the PDH, you'll get the certificate and blah, blah, blah. You've heard that before. It is being recorded. Just keep that in mind. But please ask questions, and let's have some fun tonight. And that's the name of the game. And I'm sure if we prod him, Rich will tell some of his famous jokes. He is known for his jokes. They are world famous. And some of you, I see some names here that have been to our facility. So you may have heard some of these. So just don't type in the punchline. Make sure we wait till the end on that. So I think that's enough from me for now. Hopefully I'll stay awake. I'm sure I will. I'm just kidding. But nonetheless, my good friend, Rich Medairos, take it away, my friend.
Well, great, Brett, thanks so much for that introduction. Hopefully everyone can hear me and they can see the screen okay. Just to make one last check, if you could just type in the, is it the question?
AHR was killer. Gino says AHR was killer. I agree, Gino. That's awesome.
Yeah. So hopefully you can type in that you can hear me okay.
And someone reminded me that she is the global CEO. Global CEO. That's our good friend Jim from the Central Region. Thanks, Jim.
Global
Loud and
CEO.
clear on my end. Loud and clear. Everyone's saying it. Excellent, excellent, excellent audio. Awesome.
All right, so we're going to get into it right away. Our topic this evening is Introduction to Air Source Heat Pump Systems. And actually, TACO After Dark, is it next week or 2 weeks, Brett? When do we do the next session?
No, not for a month, Rich.
Not for a month.
I will
Okay.
get the exact date.
And the next commercial focus in TACO After Dark, Brett is going to do a presentation on how to design using HSS software and
The 24th.
source heat pump.
4 weeks from tonight. 4
4
weeks.
weeks.
Yeah.
Oh, smoke, Bullwinkle.
It's because February only has 28 days, so that the numbers work out like that. You know. It's
Yeah, unless it's leap year, right? When is leap year? Is that next year?
It's not this year.
Leap year is every 4 years, I think. Well, anyway, so we're going to talk about air source heat pumps and specifically air to water heat pumps. We'll get into that. And as Brett said, please ask your questions in real time. Brett will ask me to pause periodically so we can answer your questions. And we do have time. We have the formal part of our presentation, takes about 40 minutes or so. And we're going to stay here as long as you guys want to answer questions, chat about different things, and maybe collectively as a group, we'll all learn something. And I echo what Brett said. This is an opportunity for our audience to learn something new, and also an opportunity for Brett and I to learn something new. So that's the name of the game. A quick introduction to myself. Again, Rich Medairos. I'm a mechanical engineer. I specialize in the engineering design of HVAC systems. I am a PE registered in several states, and I've been doing this for a couple of years now. So it's been a lot of fun.
And to answer one of your first questions, Rich, when is leap year? Some folks have politely told me 2024.
2024. Does it
2
every
years.
is it every 4 years?
Yes.
It
There's some clock issue, right? I think wherever that big clock is in Greece. Where the hell is that clock? I forget where that is.
Greenwich meet? I don't know. Is it Greenwich?
Yeah, Greenwich. Not Greenwich, Connecticut, though. I know that.
No, not in Connecticut. Okay. So let's talk about what we're going to talk about this evening here. Let's see if this screen works. We're going to talk about air source heat pump basics. We want to go through the basic theory of heat pumps. And then we're also going to talk about these two famous abbreviations, COP and EER, and I'll define what those mean. It's those two phrases that are used in the heat pump industry. It's as common as in the hydronic industry as GPM and feet of head. So COP and EER are real important things when it comes to heat pumps. And
I do know that sometimes when we talk about COP, EER, that's when you may need a shot of caffeine. So keep that by your phone, by your screen.
By your screen. So we're going to do a hydronic air source heat pump system criteria. We're going to talk a little bit about the criteria that we have to talk about. And then we're going to look at an HSS diagram. Now, we're not going to go into the details of the design. That HSS detailed design presentation, again, that'll be done in 4 weeks on March 24th during our TACO After Dark, and Brett will be doing that. But we're just going to show you a quick snapshot of what that design looks like, and hopefully stir some questions. And obviously we'll have some questions at the end. So this presentation isn't overwhelming. It's fairly simple and straightforward, but hopefully it will generate some dialogue and we'll get people talking about some odds and ends things here and there. Okay, so here are a couple of photographs of air source heat pumps. And these are called air to water heat pumps. And these two units happen to be manufactured by a company called Glen Dimplex. And actually moving forward, although we're not, I believe we had it at the ASHRAE show. Isn't that correct, Brett?
We did.
We had them at the ASHRAE show. And TACO is going to be launching this product in the near future. My understanding is in the fairly short near future. Can you say short near? No, that sounds like short. Right?
Yeah, but after 7 at night you can.
Yeah, yeah, because it is after 7. That's true. I'll say in the near future. I don't have the actual date of release, but I know it's fairly close. Fairly close. Okay. So let's get into a basic diagram of what I refer to as the basic heat pump refrigeration cycle. Now this is a air to water heat pump, and it's made up of these components. Let me get my pen out here. One of the major components is a compressor. I'm pointing to that right now. And modern compressors are variable speed. And in terms of most of the new air to water heat pumps that are available in the market today, they are variable speed compressors. And the piping that connects the compressor to the rest of the system is filled with a refrigerant. And I believe the refrigerant that is most common today is 410A. Can I make a little A here?
Yep.
Yeah, 410A. So let's follow the refrigerant as it flows through the piping system, and we'll start at the discharge side of the compressor. So it's connected to the compressor, and this little diagram shows the discharge. And this is the point at which the gas is compressed by the compressor. And so power goes into the compressor. And generally, we measure that power in terms of kW. And we're going to get into this a little bit later in our discussion. So that's the power input. And that's the amount of power it takes to rotate the compressor and to compress the gas. And when the gas gets compressed, it's a high temperature. I'm just going to abbreviate it here. It's a high temperature. When it leaves the compressor, it's a high temperature, high pressure gas, high HT, HP, and it is absolutely a gas. Hey, Brett, you know what that makes it? That makes it gas.
So someone just asked a basic question here. This diagram is all internal to the actual unit, correct? They just wanted confirmation on that.
Yes,
pretty much.
that's true. Yes. In terms of the modern air to water heat pump, all of these pieces, with the exception of, I'm going to kind of draw a bubble around this. This stuff is external, which is sometimes located physically inside the building, and all of this other stuff is outside the building and is contained in one enclosure. So the refrigerant leaves the compressor as a high temperature, high pressure gas, and it passes through a refrigerant to water heat exchanger, also known as the condenser. And when we talk about the term condenser, we're talking about the gas, the fluid rather, is going to be condensed from a gas to a liquid. So when it exits this heat exchanger, it leaves here as a high temperature. You ready for this? This is really cool. It's one of the magics of refrigeration. It's still a high temperature, high pressure, but it's no longer a gas. It's now a liquid.
Oh my God.
Oh my God, isn't that cool? That'll blow your mind, won't it? LIQ.
I'm blown away already.
Did I spell
Doesn't
liquid
take much though.
LIQUID?
Yes, you did. Yes, you did.
Okay. So this is one of the magic things about refrigerant. And in order to change that from a gas to a liquid, we have to remove energy. And when we do that, in this particular case, we're circulating roughly 12 gallons per minute of water through this refrigerant to water heat exchanger. And usually this is a brazed plate heat exchanger. So we're going to circulate water in here, and when the water enters, it's probably close to 110 degrees. We'll just say it's 110 degrees. 110 degrees Fahrenheit, and it's going to extract, oops, that's supposed to be Fahrenheit, Brett, and it came out looking like a goofy thing here. Let me cross that out. I'll do this one more
That
time.
was a little hard to
that was tough to follow. So this, it's entering, the water's entering at 110 degrees, is a degree symbol, Fahrenheit, F.
That's better.
That's better. So we're going to pump the water. Now, generally, by the way, it's usually, especially for colder climates, it's usually a water glycol solution. But for tonight's example, It will be a water glycol solution, but I've just labeled it water here. So the water enters the heat exchanger, plate and frame heat exchanger at 110 degrees. It extracts the energy from the refrigerant, causing the refrigerant to condense into a liquid from a gas at the same temperature and pressure, and then leaves at 120 degrees Fahrenheit. And once you have that 120 degree Fahrenheit water, you can send it out into your hydronic system to heat your building. Now, isn't that
Wow.
cool?
Wow.
Well, it's not cool, it's hot. So in a way, you can think of this whole device here, and we'll get into more of the details in a moment, this whole device here as replacing a boiler, because ultimately its responsibility is to heat water and then send that water out into the system. Now, I've used 120 degrees Fahrenheit in my example here, where we return water temperature of 110. But most modern air to water heat pumps usually generate water temperatures as high as 140 degrees Fahrenheit using this conventional compressor, variable speed compressor, and 410A. Now, there are air to water heat pump manufacturers that are experimenting with other refrigerants to get higher temperatures. But we're talking about the most common type of air to water heat pump. So they can generate water temperatures from 120 degrees to as high as 140 degrees pretty reliably.
So
and now you can send that 140 degree water out into your system to heat your building. Go ahead, Brett.
Someone, since you said variable speed, does a variable speed compressor mean the system has variable refrigerant flow?
That's true. That's absolutely true. Yeah.
Mm-hmm. And then obviously, since there's different, you could have different delta T's, correct?
Yes. So that's why I have a range
of
temperatures that you can
right.
send out. Now, most air to water heat pumps do not have the delta T that typical fossil fuel boilers have. Fossil fuel boilers can easily generate delta T's from 20 to 30 degrees Fahrenheit at the blink of an eye. But when it comes to air to water heat pumps, they're generally in the range of between 8 to 10 degrees. So if we're sending the water out at 140, it wants to come back at around 130. Or in our case, we're showing it in the black lettering going out at 120, coming back at 110. So the delta T is usually narrower in these types of systems. Okay. So now that high temperature.
Another question: what is getting the incoming water to 110 degrees?
Well, you have a device. Ultimately, let's make it super simple, and let's say you have a fan coil out there. So I'm going to put a fan, and I'm going to put a coil, and I'm going to connect from the supply water piping here. So I'll go around my balloon there up to my coil. So I've got usually copper tubes, aluminum fins, that kind of stuff. And my entering water temperature is, let's say it's 120, like I have in the black lettering, 120 degrees Fahrenheit. And let's say the air temperature is room temperature is around 70 degrees Fahrenheit. And then I want to get within 5 degrees. So I select the coil that has a 5-degree approach. And so maybe this temperature leaves here at 115 degrees Fahrenheit. Now you can sort of see where I'm headed, that if my water temperature was up around 140 and I had a 5-degree approach, it'd be about 125. So this is the air. Does that make sense? I'm putting this into a fan coil. So there's the fan. I'll label that fan with an F. There's my entering air temperature. And the fan and the coil are inside of a box. And whenever we put them inside of a box, we call them fan coils. Okay, so that water temperature has gone from 120 now down to 110 because I've given up heat into the space, and now I'm bringing that piping system all the way back. This is not the best way to pipe something, but yeah, don't try this at home. This is that old expression: if you're going to build a piping system, don't build it this way. But I
just took a picture of that and sent it to my contractor for a quote.
So anyway, so hopefully that answers the question. We're sending it out. We're just going to erase this for now because that's later. We're sending it out at 120 degrees, and we have some type of device, some terminal device. In this case, I've demonstrated a fan coil F for fan, C for coil, that's fan coil. It could be radiant floor heating. It could be special low temperature convection heaters or cabinet heaters. All kinds of equipment that's now available that runs on low temperature supply water to provide as much heating capacity as possible. Now, so
So
hopefully that answered that first question.
yeah, so the unit you're talking about isn't in a room heating and cooling a zone. This is actually producing hot water to distribute around the building.
That's correct, yeah. So the terminal
Yep.
devices could be fan coils. It could be the piping could be connected to baseboard radiation, but baseboard radiation that's designed specifically to operate at lower entering water temperature. When we think of baseboard radiation, say like from a manufacturer like Sterling or Vulcan or any of those others, they're looking for an entering water temperature between 160 and 180. Those are high temperature baseboard systems. But there are lots of new components that are available in the industry today that are specifically designed to run on low temperature entering water temperature. So in our case, we're doing somewhere around 120 degrees. Remember, your space temperature in the wintertime wants to be around 68 to 70 degrees, so you have plenty of delta T to heat up your space. But you have to have enough surface area in your terminal unit to make use of that low temperature distribution. Any other questions?
Just a couple comments. I think they're just suggesting some manufacturers that may be making this type of product: Heating Edge 3 and Slant Fin.
For the
But anyways,
yes, for the low temperature distribution units.
yeah, yeah.
Yeah, I was up in where was I? I was in Alaska a few years ago, and uh, they had these really great, I would call them cabinet unit heaters. They actually had fairly a robust surface area. So in a, you know, in a typical baseboard, it's like a 3/4 inch copper pipe or tube, and it's got aluminum fins on it, and then it's rated by so many BTUs per linear foot. And these units had a cabinet with multiple tubes in it. And what I thought was really cool was they used fans from computers to move the air across the coils to increase the surface area and the heat transfer. But you know the computer fans that are in your not in your laptop, but in your desktop computers, the ones that are about, I don't know, about 4 inches in diameter. And so they had them located on the top. It was really cool, very, very quiet, very, very efficient, and they did a lot. They put out a lot of BTUs for a relatively low entering water temperature. So yeah, there's all kinds of equipment out there today. Any other questions?
Nope. We do have a
Okay,
gentleman on from Alaska.
we do. Who's on from
Yep.
Alaska tonight?
It's not a rep, Gino. That's all I know, Gino. South. He says baseboard is king over here in Alaska.
Oh, there you go. Okay, so we've just described what happens to the refrigerant, and it gives up its heat to the water by condensing, and now we have a high temperature, high pressure liquid. And through the magic of the refrigeration process, it then passes through an expansion valve, which in its simplest form, in its absolute simplest form, is just an orifice. In the more sophisticated devices, it's actually a valve that opens and closes based on the discharge temperature of the evaporator. But we're just going to think of it as a very, very simple device like an orifice. And when it passes through that orifice, it changes from a high temperature, high pressure liquid to a low temperature, low pressure liquid. And then it enters the evaporator. Now here's where the fun starts. This temperature of the liquid has to be lower than the ambient temperature. So if the ambient temperature is 17 degrees Fahrenheit, the refrigerant temperature entering here might be, I'm just going to kind of give you a number here. It doesn't necessarily have to be this exact number, but might be 0 degrees Fahrenheit. So the refrigerant is entering the evaporator as a liquid, and it's actually extracting heat from the air. In the air, even though the air is relatively cold, 17 degrees Fahrenheit, the refrigerant is colder, so it actually causes the refrigerant to boil, because this temperature, 17 degrees, is much greater than this temperature of 0 degrees. So the refrigerant boils, and another name for boiling refrigerant is evaporation. So now the refrigerant evaporates and it absorbs heat from the ambient air. And in this case, the ambient air is 17 degrees Fahrenheit. Now, modern uh, air to water heat pumps can extract heat from the ambient air as low as around -5 degrees Fahrenheit, which is amazing. The new technology that's out there today is just absolutely amazing. So yes,
I wish I could extract heat from 17 degrees or -5 degrees, because the price of oil is driving me to bankruptcy. Let me
it
just
is.
say that.
It's
To heat
and
my
we're
home.
actually going to get
Hey,
into that in a minute. We're actually going to,
holy moly.
yeah. Well, we'll talk about that. Okay. So now it's when it leaves the look at this. It leaves the evaporator. The refrigerant is now. You ready for this? It's now a low temperature. I'm going to put the letters low temperature and low pressure gas. It's a gas.
Ay,
Low
ay, ay.
temperature, low pressure, and now it's a gas. It's very important that it leave the evaporator as a gas because we want it to enter the suction side of the compressor. So it's entering the compressor here as a gas. If it enters the compressor as a liquid, liquid is incompressible and you could break the compressor. So therefore, we have to have enough surface area in the evaporator to ensure that the refrigerant leaves the evaporator as a superheated gas, so slightly above the saturation temperature. And the way we do that is by putting a temperature sensor right here and then connecting that to a modulating expansion valve down here. And so if the temperature is not high enough, uh, so to ensure that it's a gas, a superheated gas, then the expansion valve will be adjusted accordingly to ensure that we wind up with a gas in the suction side of the compressor. So there we go. There it goes. From a low temperature, low pressure gas, goes through the compressor and becomes a high temperature, high pressure gas. And that completes the refrigerant cycle in its most basic form.
There's a lot of
And
stuff going on inside that box.
ultimately, we are extracting heat from air that's around 17 degrees Fahrenheit and generating hot water that's around 120 degrees Fahrenheit. And that's the magic of an air to water heat pump. Isn't that exciting stuff?
Yeah. So extreme condition, like -15 degrees, not a good application, right?
Well, each manufacturer rates their heat pumps based on, for air to water heat pumps for the heating capacity. Because it's a heat pump, by the way, it's reversible. I'm going to show some diagrams of that. So they are specifically designed for certain outdoor or ambient temperatures, and they have different strategies. So in other words, you'd have to have a fairly large compressor. The lower the ambient temperature for the same supply water temperature, the more work the compressor has to do. So there's a trade-off between how big and how efficient the compressor is. So to ensure that you always have enough capacity, some manufacturers will put electric resistance heater inside of their cabinet. And I'm just going to arbitrarily draw a little box here and make this an electric. Here's a couple electrical connections right there. See those electrical connections, Brett?
Yep.
And
They
inside
look like a
here
plug.
is a heating coil. And the control system will say, hey, you know what? My ambient temperature is so low, it's not a very efficient way of making heat from my compressor. So I'm going to shut the compressor off and run my electric resistance heat. So I'm going to put an RH here, RH for resistance heat. Now remember, the whole goal of these new air to water heat pumps is electrification. In other words, that we're not going to heat buildings using fossil fuels. It's going to be 100% electric. So if we don't have enough capacity because of the ambient temperature being so low, we can supplement that with resistance heat. But we only need to do that a few hours out of the year because the overwhelming majority of hours will be handled by the compressor. Put a big check mark here by the compressor. So that's how you compensate for lower ambient temperatures. And again, different manufacturers have different approaches and different size compressors, and it affects the cost, the efficiency, and the ability to extract heat from colder and colder airs, colder and colder air. Hopefully that answered that question.
Yep.
Okay, before we go on, any other questions, Brett, that have popped up?
Someone asked about cooling. Jonathan's from Alaska. I've got two others, but let's move forward.
Okay. Is it okay to race this? Maybe it'll be obviously available in the recording, but maybe someone wants to take a quick snapshot. I know I made a lot of notes on it, but hopefully as I talk through each note, you know what I was talking about.
Yep.
Okay, so we're going to erase this screen here. Erase all drawings. Look at that. Just the
Holy
magic.
moly, that was quick.
That was quick, wasn't it? Okay, so
That
let's
wasn't
go.
a chalkboard eraser, that's for sure.
Yeah, you're right. Okay, so here's now where we demonstrate the ability of a heat pump. Let me go back one slide. Keep in mind that in the heating mode, the outdoor unit, that's this guy on the left, is called the evaporator, and the indoor unit is called the condenser. Now, in a heat pump, one of the reasons we call them heat pumps is that we can actually reverse the cycle, and that's what this next diagram shows. So let's look at the unit on the left is pretty much the same that I just talked about. It has, well, no, I'm sorry, the one on the right. It has an indoor coil that's going to heat the space. And there's the compressor. Compressor is going to have a high temperature, high pressure gas leaving, going into the condenser. It's going to give up its heat. In this case, this is an air-to-air heat pump. But the one we just showed you, instead of having an air-to-air heat exchanger, it has an air-to-water heat exchanger. But anyway, that's how it generates its heat. And then it goes through the expansion valve and then through the evaporator. And this would be the same as the one we just showed you, in which case it has an outdoor air-to-refrigerant evaporator. And then it comes back through this valve here into the compressor. Now, this is the known as the reversing valve. Now, if you look at the diagram on the left, you see what happens here? They rotated. Let me see if I can get my pen out again here. There's my pen. Okay, they have rotated this reversing valve in this little diagram. They've rotated it approximately 90 degrees clockwise. Oh, I'm sorry, counterclockwise. Did I screw that up? I did, didn't I, Brett? I can't tell the difference between clockwise and counterclockwise this late at night. Okay, so they rotated this counterclockwise, and when they
That's
did
counter.
that, oh, I did it wrong again. Oh God, this is don't stay up late. This is the original one here. I'm pointing to the original.
In order to get that red thing down on the
right side, I have to rotate
clockwise.
this clockwise, and when I do, locate it clockwise. Yeah, now I have it right. Then this valve changes over here. So now the compressed gas, instead of going to this unit on the left, it goes to this unit on the right. So in which case, this is the outdoor coil, in which case it is rejecting heat to the atmosphere. And then on the indoor coil, it is absorbing heat. So this one on the right would be in the heating mode. I'll put H for heating mode. And the one on the left, exactly the same unit. The only thing we're doing is changing the position of the reversing valve. They don't all look like this. They're usually a sliding valve. And this is a cooling unit. So we're cooling the inside. So there's the indoor coil. We're cooling the indoors. And here's heating. That's because we're heating the indoors. And the refrigerant cycle is exactly the same, except we're changing the direction of the refrigerant, causing the indoor unit to go from a heating unit to a cooling unit. And that's how we can get heating or cooling out of the same device. Any questions about the reversing valve and how you can easily make a heat pump do either heating or cooling?
Oh, it's clear as mud.
Clear as mud. That's what we try to achieve here. We try to achieve mud level of quality here. All right. Let's see. Do I have another
valve
diagram?
also used? Wait, we do have. Is this valve also used for defrost? I don't know what that means.
Yes. Okay. So some manufacturers will use the reversing valve to cause the outdoor unit. Remember, this is the outdoor unit over here. And the outdoor unit, when it's in the heating mode, is actually extracting heat from a very low temperature. So the air is going across this coil, but it can freeze up. In which case, they reverse the reversing valve and put hot refrigerant in the outdoor to melt the ice or defrost it. Some manufacturers use that methodology. Others use an electric resistance heater to heat the outdoor coil. So the defrost cycle changes depending on the manufacturer and the strategy that the manufacturer is using. But yes, all heat pumps that use the ambient air as a source for extracting heat do have to account for the outdoor unit generating ice, and they have to have some kind of de-icing or defrosting cycle in their system.
Yep.
Does that help?
Yep.
Okay, so let's now talk about some of the terminology here. We're going to talk about COP and EER. COP stands for coefficient of performance, and here's the weird thing. COP is generally used to rate heat pumps. In Europe, I believe they only use the term COP. In the United States, we use both. The COP stands for coefficient of performance, and it's the ratio of useful heating or cooling provided divided by the work required. So let's go into this a little bit more. So in our case, it has to be in the same units. So for the rest of the world, the United States is a little bit bizarre, but for the rest of the world, it's generally in kW. And so we're looking for how much kW can the unit produce in heat, useful kW, and how much kW is it using to produce that heat. So it's the ratio of the useful heating, let's say it's the output capacity divided by the input power. So that's what we're talking about. It's the output capacity generated divided by the energy input, and they have to be in the same units. All right, so let's do a quick example here. Let's say we had given the following. Let's say we had 45,163 BTUs per hour, and we wanted to, with the energy input of 5,510 watts, we want to find the coefficient of performance. So it's basically the output, the capacity, divided by the energy input, but I have to be in the same unit. So I have to convert first the 45,163 BTUs into kW, and I have to convert the input power, which in this case is 5,510 watts, into kW. Once I get both the capacity and the energy input into the same units, I simply divide by those two, and that's what gives me the coefficient of performance. Okay, so here we go. You ready? Here's the 45,163 BTUs per hour divided by 3,412 BTUs per kilowatt hour, and we do that mathematical magic. It comes out to 13.24 kW. So that's the capacity of the unit. That's the ability of the unit simply to generate 45,163 BTUs per hour converted into kW. So kW and BTUs per hour is the same. It's energy. It just happens to be in different units. So now we have it in the kW. Well, what about the input? Well, the input is 5,510 watts. If you divide that by 1,000 watts per kW, magically that comes out to 5.50 kW. Now if you divide the 13.24 divided by 5.51, that's the capacity divided by the input, we have a COP of equal to 2.40. Now wasn't that simple?
Ah, piece of cake.
Piece of cake. Anybody have any questions about that? This is the fundamental math that we use when we calculate the capacity and the efficiency of a heat pump. COP, coefficient of performance.
One of our friends from Alaska says easy peasy.
Easy peasy, lemon squeezy. Anybody squeezing any lemons tonight? Somebody maybe is making a cocktail.
I'm sure they are. They might be having a cocktail.
Yeah. Well, after this presentation, I'm going to have to drink something very convincing to keep themselves from going cuckoo. Okay, so this is important stuff. I know it's dry, and I know it's math, and I know it's formulas, but it's very simple. It's very straightforward, and hopefully everybody gets it. Any questions before I go on?
No.
Okay, so you can look on a table. So I took this information from a table, and I just did the arithmetic, and it came from this table right here. Let's see, do I have any? No, I don't. Okay, so let's look for that capacity in terms of the heating capacity. And I just said the heating capacity was, let me go to that previous, oh, I'm sorry, the cooling capacity was 45,163. So over here on the right-hand side, in order to supply 42°F water at an ambient air temperature, this is the energy, the air outside, I am going to have a capacity of 45,163. And there's the watts, 5,510 watts. And if you use that formula that I just did, you'll come up with the same COP that's in this chart. Isn't that cool? So that's where that number comes from. It's simply the output capacity divided by the input in the same units. So you have to convert them all into kW. And once you do that, you divide those out just like I did in that previous page here. You come out to 2.4 as the coefficient of performance.
So whoever did this chart, did it use the same formula you used?
That's right. Isn't that magic?
There you go.
And by the way, it's the same exact calculation on the heating side. So let's pick 120° water and supply water temperature, right? So in other words, on the heating side, this unit's going to supply water. We said 120 was our case today. And let's just pick the, let's say we had an ambient temperature of 17 degrees. It would have a capacity of 28,500 BTUs per hour. So if I convert that, let's try this together, Brett. You ready?
Yep.
Oh, this is really cool. So we're going to take this one here, and I'm just going to put a little arrow here. Let's see if our arithmetic comes out correctly. So we have 28,500. 28,000. These aren't the best numbers in the world, are they, Brett? And we said, how do you 28,500? And how do you convert that into kW? Divide by 3412. 3412. Okay, and if has anybody got a calculator? Can they do that? While they're doing that, look for the answer, Brett, and I'll do it on my calculator. 28,000 divided by 3412. That converts that into kW. So I have, anybody got an answer? Nobody's
no typing yet.
Nobody's putting in a number. Let's
Nope.
see if they come up with the same number that I just came up with. 8.35. Did anybody come up with that number?
Oh, yep.
And that the units again would be kW.
Alicia did.
Okay, and I'm going to kind of make this a shortcut here. So that's this 28,500 divided by 3412 BTUs per kilowatt hour. And then I divide this number by 5,249 watts. So since the units are watts, I know if I divide the watts by 1,000, 5,249 would be 5 point, just converting that in my head, 249, right?
Yep.
And that's also in the units of kW. I haven't done this before, Brett, so if this doesn't work out, I'm going to look like an idiot. Okay, so I'm going to take that 8.35 divided by 5.249, and I'm going to come up with a COP of 1.59. 1.59. That's what my math just did. There's my COP, 1.59, and that's the COP.
Pretty close to what they show in the chart.
What do they show in the chart? Oh my God. They came up with the same number that I came up with. Wow, this is like so exciting. I'm just like I can't believe it. I'm jumping up. You can't see me, but I'm jumping up and down in my chair. No?
You're doing awesome.
I am doing awesome. Okay, so let's take a look at the chart on the heating side. So let's take a look at the chart on the heating side. Look what happens to an air to water heat pump as the ambient temperature goes up, see how it goes from 17 to 32 to 47? Look what happens to the COP. The COP also goes up. See that? Now that's
Makes
important
sense.
because what we're saying is that when the ambient temperature is 17 degrees out, we get 1.59 times the input. In other words, our output is going to be 1.59 times as much as our input. If we have an ambient temperature of around 32 degrees, you can see that increases significantly. If we have a supply water temperature that's lower, look what happens to them when the water temperature goes down, the COP also goes up. So it goes over here from 1.59, if I'm trying to supply 120 degrees Fahrenheit with an outdoor air temperature of 17. If I'm only trying to generate 100 degrees Fahrenheit with an outdoor air temperature of 17, look what happens to my COP. It increases significantly. So what impacts the COP? And let's make the obvious statement here. It's the discharge water temperature and the ambient temperature. The higher the ambient temperature and the lower the discharge water temperature, the higher the COP. This is important because when we talk about heating systems that run 12 months out of the year, the low temperature ambient conditions only take place about 5% of the total heating hours in a year. The majority of the heating hours, let's just take the Northeast, for example, the majority of the heating hours, the ambient temperature average on a daily average is around 30 degrees Fahrenheit, which means that if you have a very low temperature distribution system and you can live with 100 degrees discharge water temperature, you can have a significantly efficient unit, because if your average temperature is 32 degrees, you're going to get 3.45 units of heat for every unit of electricity. And you can see what happens in the mild weather. You still have to provide some heat. Let's say your outdoor air temperature is 47 degrees. Look at this. The COP jumps up way up to 4.16. So that's why heat pumps are so attractive, especially when we're talking about electrification, because the majority of the hours that they operate in more reasonable ambient temperatures, and they can discharge relatively low temperatures if the distribution system has been properly designed and selected to operate on relatively low temperatures. That's huge. 4.1, what was that number? It's 4.16. Let me just erase all these. 4.16, yes. So you get 4.16 units of heat for every unit of electricity that you put into the system. That's amazing. That's how you read these charts. And that's how you will influence the way
you broke that down nice. It's actually understandable now.
Yeah, and it's basic physics.
It should be intuitive, but it's not, but it is, if you know what I mean.
Right, and some
once you started,
manufacturers, you know, for the same set of conditions, they'll get higher COPs because they use much more efficient compressors, much greater heat transfer surface area in their heat exchangers. And so by changing the refrigerant, let's not change the refrigerant for a moment, by just changing the operational characteristics and the efficiency of the compressor, and by changing the amount of surface area, some manufacturers can get their COPs up to as high as 5, and I've seen some that are around 6. So these systems
so
can
here,
be very, very efficient.
Victor asked a question in regards to that. What is the range of COP to consider the unit is acceptable? I mean that's a basic. It's a good question.
It's a very good
compare,
question.
I guess.
Well, you could do it on an economic analysis. There's a mouthful. Did I use that word correctly?
Oh boy. Don't get into economics too. That's just gonna we'll
Yeah,
be
that'll
here
blow
till midnight.
everybody's mind. But I'm going to answer this question at the end of the discussion. But here, let's say last week I paid, I don't know what you paid. I think you told me, Brett. I paid $3.50. I paid $3.50 per gallon. $3.50 per gallon for home heating oil.
Yeah, that's not for gas for his car. That's to heat his house.
That That's $3.50 per gallon for heating oil. Heating oil. Yeah. HEAT. There you go. Am I spelling this right? Heating oil.
Yeah, you spelt it right.
ING. Yeah.
This
Okay.
is a
So
really sore
heating.
subject for me.
I know. It is for all of us. But wait till you see this. Okay. Let's assume that that's what you had to pay for heating oil, $3.50 per gallon. I'm not going to give you all the information. That's why we're going to do this after the presentation, because we're going to go into some detail. And what if you were buying electricity? Electricity, okay? Let's say you were buying electricity for 20 cents. 20 cents, that's 0.20 dollars per kilowatt hour. If this is what you were paying for electricity per kilowatt hour, because BTU and kilowatt hour are the same. Kilowatt hour, that's a dash, by the way, kilowatt hour. If you're paying, that's an R. Ugh, it's not the best R in the world. Kilowatt hours. If you're paying
Close enough.
20 cents per kilowatt hour for electricity and $3.50 per gallon, let's see, that's three. Oh, I have to put the words per gallon in there, per gallon. What would your COP, your heating COP, have to be in order to make the cost of heating with electricity equal to the cost of heating with heating oil? That's the problem you have to work on, and we'll answer that at the end of the formal discussion, because it'll take a little time to go through the math. But that's the example. I'm paying three, and by the way, this is what I'm paying. I'm paying 20 cents per kilowatt hour and $3.50 per gallon. So what would my COP have to be in order for the electricity cost to be equal to my heating oil costs?
So here's an answer to that question. Acceptable is the one. Acceptable COP is the one with which will meet the higher than the COP the energy code requirements.
Say that again in English words.
Yeah, acceptable. So the question was, what is an acceptable COP, right? Or acceptable is the one which will have the higher COP than the energy code requirements.
I think I understand what they're saying. They're saying that there's a minimum
So
COP
what they're saying is, if
by,
there's an energy code, that says the COP has to be 3, then acceptable is higher than 3.
correct. Yeah.
Yeah.
But for my example here, I'm just trying to figure out what's the equivalent.
Right.
What would my COP have to be in order to make my cost of heating with electricity equal to the cost of heating with heating oil? And we'll get, again, we're going to answer that question later on, but that's the problem to solve. So for all you number crunchers out there, work on that, and then we'll talk about the answer later. I better write this down. $3.50.
I need to repronounce someone's name. I mispronounced it. It's Elisha. Elisha. E-E-L-I-E-Sha. Elisha. She answered one of your questions, and I said it wrong.
Okay. 20 cents per kilowatt hour. Okay. You ready? Any other questions before I go on to the next?
Does the COP take into account the actual energy to run the unit itself?
Yes, it does. Because remember, the formula is based on the energy input, which is a part of the COP calculation.
And the 42-degree supply water on the cooling side comes from the system, correct?
Yes, if you're designing your cooling system to its capacity is based on an entering water temperature of 42. If you notice, they give you a range here in this manufacturer from 42 to 47. You could design an HVAC system that has an entering water temperature of 47 degrees. Most of the time, it's around 44 degrees. 47 would be a bit borderline in some areas that have to do a significant amount of dehumidification. But you could still do it. It just becomes expensive in terms of surface area. Okay. Are we all set to move on?
Yeah, you can move on.
All right. You didn't seem that enthused, Brett.
Well, the oil price is driving me crazy. Well, if I buy a bunch of electric heaters and plug them in and turn them on, I'm going to create a fire hazard, and I can't convert my house to all electric heat. So,
Oh
you know,
God.
but
So
don't get me
here's
going. Don't get me
here's a
going.
chart. This little graph rather represents the same thing that we saw in the chart. And I just want to show you that for an ambient temperature of 95 degrees, all right, and we had this dashed line here, that meant that we needed 42 Fahrenheit water. At 95 degrees and 42 Fahrenheit water, we go to the right and it shows over here a COP. Remember we calculated 2.4. Well, you can kind of see that 2.5 would be just above that, so I've estimated that and I call that 2.4. And so you can see graphically what happens is that as the ambient temperature begins to increase, the COP begins to decrease. So if we were trying to make 42 water with 105 ambient temperature, you can see our COP would be maybe around 1.6 in that order of magnitude. Okay. Okay, this is really the same chart, and I want to skip over that. So this is the heating. This is the heating. And again, this is what we talked about a minute ago. We calculated 1.59, and there's 15 ambient temperature. And if you'll notice, this line here represents the 120 supply water, whoops, just 120 supply water temperature. So that means it has a capacity at around, that's 15, that's 20, that's about 17, halfway between the two, a little less, a little more than halfway, be 17.5, but we'll use that. And we come up here, you can see that's 24,000, that's 28,000. Let's see, that should be 8 between the two. I'm sorry, 8 between the two. That means, yes, 28,000, a little bit above 28,000. So just above that's the same number that we used before. And again, graphically, you can see what happens. As the ambient temperature begins to drop, the COP also begins to drop. But look what happens, this is the opposite end. If we had a supply water temperature like we showed a minute ago, 100 degrees Fahrenheit, and we had a 47 degree way out here, our COP would be above 4. Now, so again, some of the manufacturers, these lines are a little bit steeper and you can get COPs as high as 5 or even higher than that. So that's what it looks like graphically.
I mean, Dan made a good point. The best design is to keep your supply water as low as possible, as long as it can heat your house.
Right. So yeah, exactly. So when you're starting to think about these types of systems, you have to think about what do the terminal devices look like. And certainly 100 degrees is more than enough temperature if you had a radiant floor heating system. But if you're using some type of cabinet unit heater, maybe with fans like I described with the computer fans in it, you'd have to have enough surface area so that you could provide heat. Because remember, 100 degrees Fahrenheit, that's more than enough to provide heat for a space that only wants to be like 68. I can't keep my house much higher than 68 in the winter. I'm probably warmer, keep my heat higher than most people do it. If I go much higher than 68 degrees, it's just too damn hot in the house in the wintertime. Especially when you come in from the outside, it's like, like today, it's like 22 degrees outside. And I come in the house, if the temperature inside the house is 70, I feel like I'm gonna die because it's so hot. So I usually keep it around 67, 68 degrees. And so, with 68 degrees and 100 degree supply water temperature, you can easily heat a house if you have enough surface area in your terminal devices. So it's all about design.
Yep.
Okay, what are we going to talk about next? Let's talk about the other value that's out there, and it's called the energy efficiency ratio, or EER, and this is the one that drives me crazy. And I think that in the United States is about the only place on the planet that actually uses this term. It's exactly the same term as COP, except it uses different units. This will drive you nuts. The capacity is in BTUs per hour, and the input is in kW. Only in America would they come up with a weird number like that. So in other words, it's the ratio of useful cooling provided divided by the work required, same exact concept as before. The capacity, however, is in BTUs per hour, and the energy input is in kW. So if we give 7,400 BTUs per hour, and we have an energy input of 456.7 watts, the EER is 7,400 divided by 1,000, because we want to convert it into thousands of BTUs per hour, and that's 7.4 MBTUH. The energy input is in kW, simply divide that by 1,000. Now you get the energy input, so you divide 7.4 divided by 0.4567. This doesn't keep you crazy at night. It comes out to 16.2. So, if you want to find out what the COP is, divide 16.2 divided by 3.412. So let's do it. 16.2 divided by 3.412, and the COP is 4.7. So COP can be converted into EER and vice versa, but only in America do we use this silly thing called energy efficiency ratio. So that'll drive you nuts. It's just a different way of saying the same thing. And in some of the charts that are out there, here it is right in front of you. So here's a chart from one manufacturer. And if you'll notice this column over here, it says it's a calculation that we just did. There's the EER. And there's the value that we did. So it has an output capacity of, there's the total capacity of 7.4 or 7,400 BTUs per, or MBPH, which is 7,400. 7.4 divided by 0.5, and they rounded up, by the way, when they did this chart. The actual number is what I said a moment ago. Let's go back here. How come I can't, oh, I know why, because I keep pressing the wrong silly button here. Okay, so I'm using 456.7 or 0.4567. They rounded it off in the chart to be 0.5, but if you do the calculation, it comes out to 16.2, and you can see right there the EER is 16.2. So only in America do they use this silly value here of 16.2 for the EER. I don't know. Maybe they just like bigger numbers to make it sound bigger.
Yeah, it's sale numbers.
Yeah, I don't know why. There was probably a reason for it. I'm sure there was a reason for it many, many years ago when people first started manufacturing heat pumps. Maybe it's because the units, people were used to using MBH and stuff like that. But so you know now that COP, the only difference between COP and EER is if you take the EER value divided by 3.412, you'll get the COP value. So it's just a different way of saying the same thing. I don't want to spend a lot of time on it because it's kind of goofy. Okay, so let's look at a diagram. Oh, let's look at criteria first. So first we need to know what the load is when we're designing a system. Then we need to know what the ambient air temperature is. We need to know what the supply water temperature is, the return water temperature, and the fluid. And in our case, we'll just say it's water or water glycol. That's rather than some kind of exotic fluid. We also have to know the flow of the fluid in gallons per minute. So let's design a system. Let's say we had a load of 180,000 BTUs per hour. We had an ambient air temperature of 0 degrees Fahrenheit for winter and 95 degrees Fahrenheit for summer. Supply water temperature of 130 degrees for heating, 45 degrees for cooling. Return water temperature 120 for heating, that's a 10-degree delta T. And a return water temperature for cooling of 55. Notice, this is an important piece here. I don't want to skip over this part too quickly, that the delta T for heating and cooling they're both 10 degrees. Now, in a conventional hot water heating system, typically if you're using fossil fuels in modern hot water heating systems, the delta T can be 20 or 30 degrees. Some people have even designed them as high as 40, but the more common numbers are between 20 and 30. But in a water source, in an air to water heat pump system, the water temperature is around 10 degrees for both the heating and the cooling. And when you do that, the GPMs wind up for the same capacity to be virtually the same GPM. Any questions about that? That's kind of a subtle thing out there, but it's an important piece.
Nope.
Okay, and in our case, we're going to do 30% propylene glycol, and our flow is around 36.5 gallons per minute. And if you want to do the arithmetic out, if you take 180,000 BTUs per hour divided by 500 divided by 10, it comes out to 36. When I did the actual calculation, accounting for propylene glycol, it came out to 36.5. And this is what the diagram looks like. So I'm going to provide, and again, what we said at the beginning of this discussion is Brett's going to go through this design software in detail. So I'm just showing you what I did. I picked 4 air to water heat pumps. You can see the temperatures. I don't know if you can read them, Brett. They're kind of small, but there's 130 leaving, 120 returning for the heating. When it's in the heating mode and when it's in the cooling mode, we have 45 leaving and 55 returning, 10-degree delta T on both sides. And if you go to the main circulating pump, I divided this, by the way, these pipe valves at the bottom left-hand corner, they continue onto the next screen. And so we have all of this wonderful stuff. And there are those valves again. And these are the terminal devices. And again, look at the entering water temperature, 130 degrees entering, 120 degrees leaving. And the GPM is 36.5. You can see it over here on the left, 36.5 gallons per minute. Whenever you do these systems, by the way, you always pick the higher GPM. So this particular calculation calculated the GPM for the cooling to be 35.9 and the heating to be 36.5. But in the real world, we would just stick with 1 GPM for this type of system, and which would be 36.5 GPM. And this gives you an idea of what the indoor units look like. These would be the terminal devices. And again, these would be designed for an entering water temperature of 130 instead of the more traditional 180 or 200 degrees. And that's the important thing. You always have to keep that in mind, that you have a lower entering water temperature, so your terminal device has to be selected for 2 things, for a low entering water temperature and a relatively narrow delta T. So in this case, 130, delta T is 10. That's the main difference for terminal units on a air to water heat pump as compared to a fossil fuel boiler, which is typically around, could have an entering water temperature of 160, return water temperature of 130. That's with a 30-degree delta T. So these are low water temperatures and narrow delta Ts. And that's the system, how the system is configured. So we've covered a lot of territory. I went over the little diagram very quickly, more to generate questions, but Brett's going to go into the HSS software in some detail. And guess what, Brett? This is where we talk about any last minute questions before, and we're, by the way,
we got some good questions here. So here's a question. And I'm not sure we're going to be able to answer it totally, but maybe partly. What is the largest capacity of a heat pump we can get in the market today, which would also be meeting the New York City code, which I'm sure we don't know what it is, but anyways.
Yeah, the New York City code is relatively new. I think they made that announcement a couple of months ago, didn't they, Brett?
I believe so.
For new construction in certain categories, the New York City code is only allowing electrification. They're not allowing fossil fuel anymore. But I believe it's restricted by category. So there are exemptions to that rule. So what are the capacities? I know what the capacities are on the residential size equipment, but I haven't seen all the capacities that are out there for commercial equipment. But residential is the capacity is around 5 tons per unit, roughly 5 tons per unit. What the capacity is on commercial equipment, most of the commercial equipment is literally being developed as we speak. So I'd have to see what the different manufacturers are providing for large commercial equipment.
Someone said, well, the same gentleman said December is when it came out. So like you said, it was only a couple months ago.
Yeah, it's only a couple months old, and I haven't read through the whole thing myself. I'm just aware that New York City did that. That's not, by the way, they're not the only ones. In Massachusetts, I think it was the city of Brookline. I think it was Brookline.
Yeah.
And did that a couple of years ago. They changed the rule and said for new construction of a certain category, and a certain capacity, it had to be electrification. They could not use fossil fuel. So it's happening all over the country. California
Yes.
supposedly is going to be one of the major markets that is going to go all electric for both heating and cooling.
So from a distribution, as someone said, can you talk a little bit about distribution systems and any issues that need to be thought through, please? I really think it's the equipment, right? From that standpoint.
Are they talking about the terminal units such as fan coils, convector
Yeah.
heaters, baseboard, and
Yep.
radiant?
Yep. I think so.
Yeah. So
That's
basically,
when that question popped up.
yeah. So basically, if you're designing a system, you need to reach out to your local rep, and many of the TACO reps now provide low temperature terminal systems that are available, and they can help you through the myriad of different combinations, entering water temperatures, capacities, all of those things. But I would reach out to the reps because they're the ones that have the latest and greatest from the manufacturer. We as TACO do not manufacture the terminal units. You'd need to go to one of our reps that handles those types of devices. And there's a lot of them out there today. So, and more every day. Keep in mind, the United States and Canada lag Europe. So most of the products, not all, but most of the products are European products that are available today because they have been doing this in Europe for a significant period of time.
So here's some education for you and I, Rich, and probably many others that are on the call. That New York law is called Local Law LL 154.
LL 154. That's going to be a number that's going to be
Look
burnt
it
in
up. Look it up,
consciousness.
baby. Look it up.
LL 154. Okay, I'm going to write that down. LL 154. I wonder what the LL stands for. Maybe they could help us understand what that. What's the LL?
Local law means local law.
Oh,
LL,
local law.
local
Well, of
law.
course. How silly am I? Actually, I wear SSS, small size sneakers. But anyway,
So now, some folks are mentioning heat pumps that are used as terminal units, and that's a little different than what we're talking about today, correct?
that's correct. Yeah. So a lot of heat pumps that are physically in the market today, the most popular one that's out there in the industry today is called an air-to-air heat pump. And the outdoor unit sends refrigerant to the indoor unit, and the indoor unit is essentially a fan coil which distributes the heated or cooled air to a ductwork distribution system. We're talking tonight about hydronic systems that uses an outdoor unit to send either water or water glycol to terminal devices for heating and cooling the space.
I would to address the question here about the ones that are used as terminal units. So someone made the comment. We just changed the high rise from 545 heat pumps to chilled water fan coils. They had a lot of. They're notorious for tripping out. I believe that the heat pump manufacturers have done a heck of a job. The terminal unit heat pump manufacturers of making their products a lot better than that. That issue's not as prevalent these days. The noise and tripping out and all of that. But again, unless we know more about the design, it's hard for us to comment too much on some issue like that.
Yeah, keep in mind that we're talking about a category of heat pump that's specifically known as the water to air heat pump, and they sort of take the place of a central boiler chiller plant, if that makes any sense. And the ones that you're talking about, the terminal devices, which are typically referred to as water source heat pumps, that's when the refrigerant is in each one of the boxes and distributed throughout the building. This is basically the refrigeration process takes place outside in a box. And the refrigerant never enters the building, just the water glycol solution enters the building, and then it does all its work from there.
Now, the next session in 4 weeks, we will design with the software some systems similar to what Rich showed you with these outdoor units, but we're also going to design some indoor terminal unit heat pump systems as well that use probably your more traditional boiler cooling towers type of setup or ground source or something like that. Anyways, so what is your opinion on adding water to / heat pump as backup to existing oil hot water boiler? Does that make sense?
I'm not sure I understand the question. Maybe they could
Adding
rephrase it.
water. What is well, Gilbert? Can you help us ask this question? I'm reading it. No, what's your opinion on adding water / heat pump as backup to existing oil hot water boiler?
Oh, okay. Yes,
Anyways,
yes. We sometimes refer,
backup heat oil. Yeah.
yeah, so sometimes we refer to those types of systems as hybrid systems. You know, so what do we mean by hybrid relative to the automobile industry? We're talking about basically fossil fuel, which in the automobile industry is gasoline with a battery and an internal combustion engine electric motor. So you've got two sources of energy. You've got fossil fuel, gasoline, you've got electricity from the battery, and you've got an engine, which also operates as an engine generator set, and you have an electric motor. So you combine all of those things together, you have a hybrid system. So hybrid systems are also gaining in popularity where, especially in very, very, very cold climates, where it might be significant cost. If the farther north you go, the longer the colder periods get, and it may be more economical to have a hybrid system that with the fossil fuel runs during the coldest part of the year, which is again is only maybe 5 to 8% of the year. Well, actually, when you go farther north, it has a longer period. Maybe it's 20%. I'm just kind of making up numbers without reading the statistics from ASHRAE. But let's say it's around 20%. And so 20% it runs on fossil fuel, but 80% of the time it runs as a heat pump. So those are hybrid systems. So yes, they are out there and they're gaining in popularity. I actually designed one for an R&D project, research and development project about 5 years ago. That was a hybrid system. That used natural gas for the most severe conditions and used an air to water heat pump for the balance of the conditions. And again, because it was New England is not as severe as much farther north. When I say north, I'm talking about, because I happen to be out there and I was chatting with all the guys in Edmonton. What is that? Edmonton, Alberta? Is that where that is? Is it the
Yes.
province? If someone is in Canada, tell me if I've got the right province for Edmonton. I always get that mixed up.
You do.
But yeah, they have much longer and colder winters than we have in New England. New England, the coldest temperatures are only around 5 to 6% of the time.
They see 30 degrees Fahrenheit in the summer, not in the winter. So,
there you go.
so here's some more education from Michael. It gets even better when we were talking about the law and the new energy law, electrification in New York. The Department of Energy is beginning to seek non-greenhouse gas refrigerants. All of the hydrofluorocarbon refrigerants that I know of are all classified as greenhouse gases. So that could get messy.
Yeah, so one of the refrigerants that's being explored extensively in Europe is CO2 of all things. And so the CO2 has a couple of the benefits of CO2 is that it is, it is a global warming in the sense that, it adds to the CO2 layer in the atmosphere. But the benefit is that the system holds out the promise of generating higher temperatures. So instead of having an upper limit of 140 degrees Fahrenheit for your hydronic distribution system, they might be able to generate temperatures as high as 160 degrees. So that has an impact downstream. Again, the higher the water temperature, the less surface area you need downstream. And for retrofit purposes, if you had a unit that could generate 160-degree water versus 140-degree water, you may be able to use that as a direct replacement for a boiler. So yeah, there are all kinds of things out there that are being explored for refrigerants and stuff like that. Very
Yeah,
cool
it's getting
stuff.
scary. I'm glad I'm old. So Justin, this statement / question's been out there for a while, and I think this was when you were talking about the adding that resistant heat. So it said, and that's more efficient than putting the power into a resistive heating element. I asked them to clarify that. I don't think we're going to be able to answer that one.
Essentially, by the way, just to make sure everyone understands, so since you're talking about the COP, the output for a convention for an water to air, I'm sorry, for an air to water heat pump, the COP is greater than 1. The COP, although we don't use this term in resistance electric heat, is 1. So in other words, if the air to water heat pump has a COP less than 1, it's more energy efficient to use electric resistance heat because electric resistance heat has the same capacity output as the power input. In other words, 100% of the power can be converted into heat. I forgot to mention that.
Yep.
Okay, what next, Brett?
That's it.
That's it?
So did you ever answer your question about the 320 and the 20 cents and all that?
Yeah, did anybody do that calculation?
There was no nothing.
Nothing? Okay, so
146, someone just said. 146, Paul did.
oh, he did.
Well,
So okay, so should we take his word for it, or do we want to see the calculation? Does anybody want to see the calculator? Let's try that.
yes.
Somebody say, do the math. All right, we're gonna do the math. All right, let's pick a white sheet here, so we can do the math. I'm gonna pick a blank. There's a blank. Can you see that, Brett?
I can see a blank sheet. Well, almost a blank sheet of paper.
Okay, so let's see if we come up with a number that is close to Paul. Let's see, what's Paul's last name here? Let's look at. Oh, why can't I get this thing to expand? Oh, anyway, you'll have to tell me what Paul's last name is.
Dragich.
Oh God.
D as in dog, RAG as in goat, IC as in cat, H.
So I'm going to try
Based on
this.
1,000
So
BTUs per
Paul,
gallon, which may be off.
Paul, I'm going to try pronouncing your name. If I get it right, just give me a thumbs up or a yes. Is it Dragic or Dragic? Let's try the first one. Is it Dragic? Let's see what he
said
says.
based on 1,000 BTUs per gallon, which may be off.
Oh, well, okay. So, all right. So let's do this together. You ready? So if we have 1 gallon, let's get a pen. Where's my pen? There's my pen. Okay. So we have 1 gallon of home heating oil, 1 gallon. And the traditional value that we use for home heating oil is equal to 140,000 BTUs per gallon.
That's what Gino just typed in right here. 1 gallon equals 140,000 BTUs.
There you go. Yes, 140,000 BTUs per gallon. 140,000. I'll just put in B here, up here. Okay. So to simplify this, and I'll show you why we're going to do this, we're going to say, well, what's the cost of 100,000 BTUs of available heat? 100,000 BTUs. And the reason I'm using 100,000 BTUs is because we have a technical name for that, and that's called a therm. All right.
Yeah, you can tell, I think, in therms is what Paul just said.
Yeah, so it's 100,000 BTU. Okay, so how do we get this 140,000? Well, when it turns out, and again, we said this is a residential system. We're going to use very, very simple numbers here. If I have a gallon of fuel, I can only get roughly 80%. Now I know that boilers are a little bit more efficient, but for simple math tonight, we're going to say 140 times 80% efficiency. I'm not going to rewrite that out. So I'm going to just say 140,000 times 0.8. So that means that 1 gallon has 112 112,000 BTUs, 112,000 BTUs of heating capacity, and then that's at 80% efficient. All right, so far so good?
Yep.
So if I want to convert this into, and again, we said a gallon was $3.50. How much would 100,000 BTUs or 1 therm, what would that cost? Well, we simply take the ratio of 100,000, 100,000 divided by 112,000 times 3.5. It would cost me, whoops, I really screwed that up, Brett. 100 divided by 112 times 3 point, jeepers creepers. I'm having tough times pressing the
That's
buttons
after
on my,
8:30, so.
that's why. Times 3.5, it's going to cost me $3.12. $3.12. I'll make it 13 to round it off. $3.13 in order to provide 100,000 BTUs from heating oil. $3.13 for 100,000 BTUs. So far, so good?
Yep.
Okay, so how much electricity do I need to consume in order to generate 100,000 BTUs? Well, I would take 100,000 and divide that by 3412. And if you remember, the units for this is BTUs per kilowatt hour in order to get it into kilowatt hours. And again, that's energy. We're talking about energy here. So in other words, if I take 100,000 BTUs per hour divided by 3412, I would need to have 29.3. I'll write that down here, 29.3 kilowatt hours, or KW. I'm sorry, kilowatt hours. Kilowatt hours. Kilowatt hours. I can barely get the lettering in there, Brett.
You're getting close to the edge there. It looks like the world is flat.
It's flat. So I have 100,000 BTUs, and I divide that by 3.412 BTUs per kilowatt hour. The units are going to come out to 29.3 kilowatt hours. Well, we said that electricity costs 20 cents per kilowatt hour, so I multiply that by 0.2, and magically I come up with $5.86. $5.86. I'll round it off. $5.86. So what did I just figure out? I figured out that if I generated 100,000 BTUs with burning home heating oil at 80%, oh, I put 8 in there. That's at 80%. 80% efficient. It would cost me $3.13 to generate 100,000 BTUs for available heating. If I did it with electricity, it would be $5.86. And that's with resistance electric heat. Remember, that's with a COP of 1. So how do I figure out what the COP would need to be? Well, I simply take the 5.86 divided by 3.13, and the magic number comes out to 1.87. 1.87. Isn't that what
Paul said 4.6.
What did he say?
1.46.
Oh, okay. We'll say 1.87. So you'd have to have a COP of 1.87. There's our COP. If we had a COP of 1.87, then we would have the same cost, we're doing an economic analysis, as burning 1 gallon of burning heating oil in the right quantity to generate 100,000 BTUs. So that means that anything above 1.87 would be more cost effective than home heating oil at $3.50 a gallon. Isn't that cool?
So should we? Yep. Let's not let the politics efficiency this.
Yeah.
So,
So that's how you
Paul,
figure
Paul,
out.
Paul, Paul made the statement he didn't use the 80% gas efficiency. So if he
What did he
divides
use for gas
146
efficiency?
divided by 0.8, he comes out to 182. So
Yeah. So Paul, what did you
virtually,
use for your? Well, you have gas efficiency. Remember, this is a heating oil, so it's not
yeah,
gas.
yeah. He meant that gas efficiency is not heating oil, right? Yeah.
That's what Gino says.
All right.
Oh, this is cool. This is really cool stuff.
Now, hey, by the way, I just want you to know we had a guest, not a guest, but a one of our students tonight was John Siegenthaler.
Hey,
So
John, how you doing?
yeah, so you're under pressure here. I mean, he knows he could have taught this class, you
He
know that.
wrote the book.
So
He wrote the
I
book.
know we all have learned, probably 80 to 90% of the people on the call tonight have learned from John over the
Yeah,
years.
that's right.
He's
From
a
one
good
point.
friend of Taco's, that's for sure.
So is he still on?
He is. I don't know if he's paying attention, but he's on.
Well, if he's still on, John. So what did you think about our stuff? Did we have cover enough material tonight? Okay.
It says he's not attentive, so he may. Robert said he's the man, which is true. He is the man. But anyways,
Well, if he's the man, we're the boys, right?
yeah, there you go.
But there's two of us, so two boys equals one man.
I don't know about that.
I don't know. Well,
Yeah,
do we
I
have
think we're
any
done
other
for the night.
stuff that folks want to
Oh,
chat?
by the way, Michael, way back at the beginning when we were talking about where the time clock was, what the heck when we were talking about leap year and all that, he says that you mentioned the name of a city. It's in the UK. That's another thing we need to learn. Remember we were
Yes,
talking about
Greenwich
the
Mean Time.
official
That's in,
clock.
that's in the
Yeah,
UK.
that's it. Michael says it's in the UK. I wanted to make sure because I like to learn, because in case I make Jeopardy, that might be a Jeopardy question,
Yes, exactly.
Oh,
So here's a
well,
question for you, Brett.
are you
Ready?
talking into your? We can't hear you. Where'd you
Oh,
go?
I'm sorry. I'm sorry. Can you
Oh,
hear me now?
yeah.
I just leaned over. Okay. Um, all right. So here we go. If you're if you're standing, let's say you're floating in space. You're floating in space and you're floating about a mile above the North Pole. Which direction does the Earth rotate? Does it rotate counterclockwise or clockwise?
Oof. Well, while you're thinking of that, Lauren says, I sure love my 95% efficient gas furnace with fuel at about $1 per CCF.
That's
I'll try
correct.
to figure out COP break even later. Oh, so someone said counterclockwise and someone said trick question. It doesn't rotate.
The Earth doesn't rotate?
Yeah, he's been goofing around. Counterclockwise is what the consensus is so far.
Okay, so if you have a low pressure area, which is what we have coming up for tomorrow, overnight tonight, and does it rotate clockwise or counterclockwise?
Jeez, it is Big Ben, Greenwich Mean Time. I don't know.
If the storms, low pressure areas rotate counterclockwise in the
There you
northern
go.
hemisphere, and low pressure areas in the southern hemisphere rotate clockwise. Little trivia.
Which way does my snowblower rotate?
Your snowblower rotates forward to backwards.
Oh boy,
Oh,
depends on the hemisphere. Michael said. I
that's
think we're
true.
done. Any questions out?
Any
Any other
last minute
questions? We got a lot of
questions
goofing
out there
around, but not questions.
before we sign off?
How
Any
about
last
someone said what is HSPF, and then they said heating season performance factor. Jarrett made that statement. So
Oh, that's a good abbreviation to
yep, yep,
memorize.
yep.
I try not to memorize too many too many. Oh, so Gordon says you have done
I
well.
know. Yeah,
Oh God.
that's because
Okay, so
he hears.
Gino, quick question for Gino. If propane is 92,000 BTUs per gallon, what's the cost of propane per gallon these days? He's not saying.
Gino's been answering questions and typing in all night. If I had said everything he typed in, we'd still be talking about the refrigerant cycle.
We're gonna recruit Gino for the next presentation.
He's out in Alaska. There was another gentleman out in Alaska. I think he worked for the government out there.
good stuff.
I'm
Good
not sure
stuff.
he's still on. So thank you,
Well,
Rich.
It sounds like we're just about, nobody's having any new questions. Let me, before I turn it over to you, Brett, say thank you so much for participating. Hopefully it was informative at the most basic level, and you got some sense as to what the stuff is all about. Brett will build on it when he goes through the HSS design. Hopefully you had some fun. We laughed a little bit. We made some mistakes. We corrected ourselves, and we got some input in terms of questions and answers. So
Yep.
with that, I'm going to turn it over to Brett. Say thank you very much, everyone, and Brett, take it away.
I want to clap in my headphones. Great job, Rich. I understood a tenth of the math you put up there, but for me, that's pretty good after 7. So I'm pretty that. A lot of thank yous, a lot of great job, a lot of pats on the back. Again, just so you know, it was recorded. Oh God, that's scary. Don't send that to our boss. Don't send the recording to our boss.
Don't let
Please.
our boss see it. He'll get rid of us.
Oh man,
He'll
we're
have
getting
us.
enough trouble.
He'll have us picking up trash in the parking lot for the next 6 months.
Oh boy. But thanks everybody. We'll see you in a month. And if you want to follow along and learn how to use the software while I'm putting things on the screen, you can go to our website. You had a minute to do that, Rich? Show them where they can download it on the website since your screen's there. Can
But
you
the
get on the internet?
HSS?
Yeah.
Yeah, absolutely.
So
Okay. So here we go.
If you go to our TACO website and download the software onto your computer, and make sure you have a mouse so you can follow along. It's a hell of a lot easier to use with a mouse, because I will be, kind of goofing around and doing that. But Rich is going to bring up the website right now, I think.
How come I can't go? Here's my drawing tool. Erase all. There it goes. Okay, so now I can erase all that. And all right, what is this? Oh, that's some kind of silly
Good.
computer thing.
There's
right?
that girl. She's still running.
Still running on the beach. Yeah. Okay, so here is the company website. Are we going to the HSS software, Brett?
Yeah, just show them where they can get to it.
Okay, so here is the company website.
Homepage.
And homepage, and under software, you can click there. And then you go down here where it says HSS, Hydronic System Solution. You click on that. And if you look from left to right, it's the second one from the left, Hydronic System Solution. And you can click on download. And it's going to ask you a couple of quick questions. What's your name?
So you do have to, it has to reside on your computer. It's not a web-based program. So
yeah, it's not a web-based. So you download it and put it on your desktop. You just put in a couple of pieces of information. If you want to send Brett and I an email with one of your credit card numbers so that Brett and I, I'm only kidding. We're not going to buy anything.
It's free.
It's free. It's free. So and that's
free
how
to all our friends.
Right. You put in your name. I won't do it because it'll screw up my computer. But you put your name in there. So it's pretty straightforward. One more time. There's the home page, software, HSS, and there it is. Click on that, and you go to the download and fill in this little data, press download, and you're in like Flynn, as they say.
Thank you, Rich. Thank you, everybody. We will see you in a month. 4 weeks from today. Take care, everybody. A lot of fun. Thanks for making it so much. Like we said at the beginning, we all learn. I know I learn on a daily basis, and the input we get from you folks make it much more worthwhile for all of us. So take care, and we will see you down the road. Good night, Rich.
Take care, folks.